where on the last decay, we're going to talk about gamma rays. Now, gamma rays is quite categorically different than beta decays. Quite different. And one of the things that we learned, and I think I'm going to give you an overall view first before I go into the details like we did before. And so what's special, well, here, let me just, here, let's do a brief review of the atom. And one of the things that I really tried to get you to see here is this. When we studied the quantum atom, we learned that light emitted by an atom occurs when electrons jump. Okay, when electrons jump. So if we look at this thing, we could go in here and just say, yep, let's look at this thing. And we said, yeah, here's our nucleus, right? And then we had whizzing electrons in the Rutherford model. And so when we looked at these electrons that are moving like this, we came back and we said, bad model of the atom, right? Bad model. What model really does well? It's the quantum model. So when we looked at the quantum model, we had energy levels. And let's say that we had an atomic structure that looks like this. So what am I seeing here? What I'm seeing here is that I can have an electron that then jumps energy levels. In other words, it falls, let's say, to here. And in that process of falling, there's this emitted radiation. And this guy we called light. Well, it turns out that we have the exact same type of thing. And what I'm going to do here is I'm going to still this nucleus over here. Okay, I'm going to copy it right here. So a bad model of the nucleus is this, right? That's a bad model of the nucleus. So if I come in here, and then what I'm going to do here is that I'm going to get rid of that, and I put in a proton here, I'm saying that this model is a bad model. And if you go and you look at just pictures, right? If I type in here, and I type in the nucleus of the atom, and then I just say images, just let me share my screen with you. Look at these images. Look at these nuclei. Don't they all look at that? Do you see any other picture? And the answer is no. It's a bad model of the nucleus. Just like, you know, just like the Rutherford model is. And the problem is it just gets more difficult for people to really grasp what's going on. And so what we find here is that there's a quantum model of the nucleus. So when I look at this, I would say here is that there is a quantum model of the nucleus that puts nucleons, remember what nucleons are, right? It's protons and neutrons, the combination. So it puts nucleons into nuclear energy levels. They're energy levels. So there's a structure into energy levels that are quite different. And I showed you when we looked at the actual quantum model, it's more complicated than those single model energy levels like I was talking about. But when you look at the quantum nucleus, right? So now if we look at the quantum nucleus, what you see here is that you have a structure that looks something like this, where it organizes protons and neutrons. And I'm just showing you the simplest one, where you could literally put protons and neutrons in these energy levels on one side and the neutrons on the other side. So this is a fairly easy model, and it's sort of like the model that you see here that I drew, but it's, of course, it's more complicated. So we have this quantum nucleus. And so what's really special about these quantum nuclei is we talked about binding energies already. And so what we find here is that we have these, electrons that can jump. We have protons that could jump. So what we're saying here is that, so if I now compare the energy levels between electrons and nucleons, here's what you find. Well, what you find here is that the electron has an energy level that is really, really tiny. So if I was to look at this thing, the spacing is a number called 10 electron volts. So it's by a factor of 1. So in this case, if I have an electron and this electron jumps, let's say from here to here, it's then going to emit this very, very, very low energy light. So what we're seeing here is that it emits very low energy light. Wow, in the nucleus, wow, what a huge difference. So when you look at the scales between, so now if let's say that I have a proton that's going to jump now, just like the electron. When you compare the scale from here to here, it's actually 1,000,000 times bigger. So what this is saying here is that that nuclear jumps occur 1,000,000 times higher. And because they're higher, they emit the highest energies of light. And the highest energies of light is known as a gamma ray. And the gamma ray is typically written like this here. So the highest energies are gamma rays. So if you want any type of gamma radiation, you have to deal with the nucleus. You cannot deal with the electrons. So there's a huge difference between the two. So now that I've talked about the difference to these here, we can just say one last thing. So when this thing jumps, man, we're talking, and it falls from here to here, it is going to, so there's extremely high energy light. That's why gamma rays are dangerous. Okay, that's why gamma rays are dangerous right there. So gamma ray radiation is something that people have to pay attention to. Now, I should be really, really careful because the gamma rays that we typically use in medical imaging are not as energetic, but most of them are definitely energetic. So then we should start to go, so we should answer one more question and then move on here. So now we can answer the following question. Because I've heard this question asked before, and I think it's a really good question. So why do protons / neutrons not part of chemical reactions? And the answer is, to have neutrons and protons be a part of any reaction, you need 1,000,000 times more energy. So what you're finding here is that chemical reactions, by the way, what do I mean by chemical reactions? We're talking about bonding of electrons, just like we talked about potential energy or the nuclear wells. So chemical reactions only use small energies, while nuclear reactions require enormous energies beyond chemical ones. So therefore, they're really inert. Should I say that? They're inert to chemical reactions. They just sit there and do nothing. The only way you can get a chemical, the only way you can get protons and neutrons is you need a thermonuclear process. And typically that requires a lot of energy.